ఇంటర్మీడియట్ విద్యారంగంలో అగ్రగామి మన NSR ఇంపల్స్ ఎడ్యుకేషన్ ఇన్స్టిట్యూషన్. ఐఐటి జేఈఈ అయినా నీట్ అయినా తిరుగులేని విద్యా సంస్థ NSR ఇంపల్స్.
Next, color. The next property is color, right? So how to, now first point, do they possess color? Yes, halogens, all halogens are colored, all halogens are colored. So if I take fluorine, its color is say light yellow. If I take chlorine gas, yellowish green or green yellow, something like that. Bromine, orange red color liquid. Orange red color liquid. Iodine, deep violet in gas phase and dark brown or blackish brown, you can say, simply writing brown, blackish brown to be correct, in solid state. Right, first, these are the colors of the halogen. Next, why they possess color? See, the reason for the color is based upon molecular orbital energy diagram. You can explain molecular orbital energy diagram which you have drawn for oxygen and nitrogen, right? Now here also they are diatomic molecule like O2. Now what happens here is the electrons that are present in HOMO, highest occupied molecular orbit, highest occupied molecular orbit. LUMO, lowest unoccupied molecular orbit. Once again, highest occupied molecular orbit. LUMO, lowest unoccupied molecular orbit. So this is the molecular orbit that contain valency electrons. This is the next higher energy level where there are no electrons. So here there are some non-bounded electrons. These non-bounded electrons, they absorb visible light. They absorb visible light. The electrons absorb visible light and get excited too from HOMO to LUMO. In the de-excitation process, this is the excitation process. In the de-excitation process, they emit light of complementary color. So that is why they possess color. Once again, so here we are explaining the reason for color based upon molecular orbital diagram. The valency electrons that are present in the highest occupied molecular orbital, they absorb visible light, they gain energy, right, and get excited to next higher energy level which we call it as lowest unoccupied molecular orbit. They are unstable. In the de-excitation, they emit that excess energy in the form of light. Suppose if they absorb particular light, its complementary color is emitted. So here this energy that is to be absorbed depends upon size of the halogen. Smaller the size of the halogen, greater is the excitation energy. Why? Because you are exciting the electron. This electron is bound to the nuclear attraction force. So if the size of the halogen is less, then the electron is very near to the nucleus. That means effective nuclear charge is more. So to excite that electron, you have to supply more energy. So if I take fluorine, the size of the fluorine is smaller, That means the electron is very near to the nucleus. Therefore, the energy required to excite it is more. So, here it is absorbing which light? Visible light. So, visible light is nothing but VGR. So, here fluorine absorbs violet light and emits its complementary color, that is nothing but yellow, light yellow. The complementary color is light yellow. But when I come to iodine, from fluorine to iodine size increases. If the size increases, the valency electrons are away from the nucleus compared to fluorine, the effective nuclear charge is less. Therefore, you have to supply less energy to excite that electron. Therefore, here the energy required to excite this electron in I2 is yellow. It absorbs yellow light. Now, what is its complementary color? Violet. That is why the color appears, the complementary color is violet. If it absorbs yellow, emits violet light. If it absorbs violet, emits, its complementary color will be yellow. So, fluorine absorbs violet and emits complementary color yellow. Iodine absorbs yellow and emits complementary color violet. The color of iodine depends upon solvent. That means if I change the solvent, the color of iodine also changes. Right? Once again, right? If the iodine is dissolved in different solvent, depending upon the solvent, the color of iodine changes. Let us see some examples. In presence of aliphatic hydrocarbons, in presence of aliphatic hydrocarbons, that means if iodine is dissolved in aliphatic hydrocarbons, the color is found to be same, that is nothing but violet, no change. In presence of aromatic hydrocarbons like benzene. So, here one more point, you can even write CCl4. In presence of aromatic hydrocarbons, the color changes to pink, or you can write reddish brown. In presence of solvents like alcohols, ethers or amines, the color found is deep brown. So, here what is happening? When the color changes, see here, if this energy difference is increased or decreased, the energy required to excite and energy emitted during the excitation changes. Once again, if the energy difference between HOMO LUMO is altered, then the energy required to excite the electron and the energy released during excitation will change correspondingly. Here, if the solvent interferes or alters this energy difference, then only the color will change. If I take aliphatic hydrocarbons, in aliphatic hydrocarbons are nothing but saturated hydrocarbons. They do not possess any lone pairs. So, if they do not possess any non-bonding electrons or lone pairs, they do not alter this energy difference, hence the color remains same. If I take aromatic hydrocarbons, they possess pi electrons. These pi electrons will add to HOMO, that means they occupy HOMO, not this HOMO, another HOMO, this becomes HOMO, and the next molecular orbital becomes LUMO. Because of this, the energy difference will alter. So if there is a non-bonding electrons or the electrons that are capable to occupy the molecular orbitals in the iodine molecule, then the energy difference will change. In case of aromatic hydrocarbons, they possess pi electrons. The pi electrons may occupy molecular orbitals, and the homo-LUMO energy level changes, their energy difference changes, the color will change. When I come to alcohols, ethers, amines, so they possess lone pair, alcohol, ether, amines. Oxygen possess lone pairs. Because of these lone pairs, they are better donors compared to aromatic hydrocarbons. They are better donors. In aromatic hydrocarbons, the pi electrons are involved. The pi electrons are again held by the nucleus. They are loosely held, but they are under the influence of nucleus. But these lone pairs, they are under the influence of only one atom. So these alcohols, ethers, amines are better donors. Hence, they will alter the energy levels to greater extent compared to aromatic hydrocarbons. These are non-donor solvents. They don't have any lone pairs. They are called donor solvents. The color of iodine changes with solvent. If it is non-donor solvent, then it will not change. If it is donor solvent, then it will change. So this is about the color. That. Now let us study oxidation states. We are going to study the oxidation states of elements of 7th A group. So what is the outer electronic configuration? NS2, NP5. So let us write the ground state electronic configuration first. This is ground state. In ground state you have 7 electrons, NS2, 2 electrons, 1, 2, 3, 4, 5. So you have one unpaired electron in ground state. During bond formation, generally the unpaired electrons participate in bonding. So in ground state, this one electron will participate in bonding. So it may be lost or gained. Because they are most electronegative elements compared to other group elements, they may even gain depending upon the other element. So if depending upon that, if they gain, the oxidation state will be -1. If they lose, the oxidation state can be +1 depending upon the other element. So if I go to the first excited state, so what is first excited state? One of the paired electron is excited, is promoted to next higher energy level, that is nothing but the orbital 1, 2, 3, 4, 5, right. So So this is the paired electron that is promoted to the next higher energy level. So 1, 2, 1, 2, 3, 4. So the electron is promoted from here to here. Now you can see there are 3 unpaired electrons, 1, 2, 3. The tendency to gain 3 electron is difficult, is the ability of the element to gain 3 electrons from 3 different atoms is difficult. Therefore, they may allow these 3 electrons to participate in bonding. So, in that sharing, most of the elements they have tendency to lose, or since this is single element is forming 3 bonds with 3 different atoms, let us say, so it becomes central atom. Therefore, central atom has tendency to lose the electrons. Therefore, here the oxidation state is should be +3. Next, if I go for next excited state, we have 2 more electron pairs and the empty available d orbital. So, I can promote another electron here. So, going for second excited state. So, electron is promoted from here to here. Now, you can see there are 5 unpaired electrons. So, a single atom can form 5 bonds, right? It becomes central atom. The tendency it should have tendency to lose that. So, tendency to gain is difficult from 5 different atoms. So, it should show +5 oxidation state. Similarly, let us go. Still, we have one more paired electrons. So, let us try to excite it. Third excited state. So, the expected oxidation state should be +7. There are 7 unpaired electrons. So, let us study. So, what are the common oxidation state here? -1, 0 in elemental state, +1, +3, +5, +7. So, let us start with each element with fluorine. Fluorine is the most electronegative element and it is a powerful oxidizing agent. Therefore, there is no other element which can oxidize fluorine. Fluorine always shows only one oxidation state in its compound, that is nothing but -1, and its elemental state -0. It does not show positive oxidation state. The reason is there is no other element which can pull electrons from fluorine, because it is the highest electronegative element. There is no other oxidizing agent that can oxidize fluorine. Therefore, fluorine does not show positive oxidation state in any of its compounds. It will show -1 only. In elemental state it shows 0. Next, there are no d orbitals, so there is no question of showing higher positive oxidation state. Even if it possesses d orbital, there is no other element which can oxidize fluorine. Therefore, fluorine only shows -1 in any of its compound and 0 in its elemental state. Other elements, they show all these oxidation state ranging from -1 to +7. Apart from this, chlorine and bromine, they show +4 as well as +6, unusual oxidation state, +4 and +6. So, if I take +4, example is ClO2. If I take for bromine, it is BrO2. If I take for example for +6 oxidation, there are compounds like this Cl2O6, and for bromine it is BrO3. So, chlorine and bromine also show +4 and +6 oxidation in some of their compounds. One more important point, bromine does not show +7 oxidation state. Bromine does not show +7 oxidation state. That means Br2O7 does not exist. See why I am writing only with oxygen. Oxygen is the next most electronegative element which is capable of exciting these electrons to higher oxidation state. After fluorine it is oxygen. So mostly the oxygen compounds are capable of exciting these electrons to higher oxidation state. So that is why generally we study with oxides. Why Br2O7 doesn't exist? Because although other halogen shows +7, why bromine doesn't show +7 oxidation state? Now the answer here is explained by concept called middle row anomaly. What is this middle row anomaly, right? So if I write bromine, atomic number 35 if I am not wrong, helium, neon, argon, right? Right. So middle row anomaly, this is associated with the element that is present in the middle where 3d electrons begins, where 3d electrons are present. So here if I write the electronic configuration, you can see this 3d orbital, that is 3s2, 3p6, 3d10, 4s2, 4p5. When bromine shows +7 oxidation state, if the 7 valency electrons participate in bonding, right? Now, what is the problem with these 3d electrons? The problem with 3d electrons is they have poor shielding effect, particularly this one, they have poor shielding effect. So what happens? Because of poor shielding effect of 3d electrons, the effective nuclear charge, that means the net nuclear charge on these 4s2 electrons is high. So when it will show +7 oxidation state, when this ns electron is promoted. So we are talking about this ns2 electrons, 4s2 electrons. Due to poor shielding effect of 3d electrons, 3d10 electrons, the effective nuclear charge on 4s2 is very high, higher than that is expected. So we can supply that energy, but that much amount of energy must be compensated during bond formation, which doesn't happen here. The energy required can be supplied externally, but that must be compensated, that must be released during the bond formation. Then only the compound formed will be stable, otherwise the compound is unstable. Once again, due to poor shielding effect, the net effective charge on 4s electron is much higher than that is expected. So you have to provide more energy to excite 4s electrons so that it shows +7 oxidation state. This energy we are supplying externally, but that much energy should be compensated during the bond formation in Br2O7. Then only the compound is formed and the compound will be stable. If that energy is not compensated by bond formation, if that much amount of energy is not released during bond formation, the compound formed is highly unstable and will be decomposed. So here that doesn't takes place, that doesn't happen. That means during bond formation, the energy released is not sufficient enough to compensate compensate the energy required to excite 4s electrons. Why you require more energy to excite 4s electrons? Due to poor shielding effect of 3d electrons. Does this happen with other elements? No. The reason is d electrons are present only in bromine. In other cases, the compensation may take place, but in the middle element, wherever you have 3d electrons, middle element fluorine, chlorine, bromine, then you have iodine, astatine. So between top two and last two, bromine is middle element where 3d electrons are present. So that is why we call it as middle row anomaly. So bromine doesn't show +7 oxidation state. So this is about oxidation states. So the next one is oxidation potential. Halogens are powerful oxidizing agents. Powerful oxidizing agents. What is an oxidizing agent? It oxidizes some other substance. So what is its oxidation state? 0. Here it is +1. So there is increase in oxidation state. So this substance is oxidized. X is oxidized. By what? By this oxidizing agent. So what it is doing? It is losing electron. The electron is gained by oxidizing agent. The oxidizing agent itself will undergo reduction. Why they are powerful oxidizing agent? Because they contain 7 valency electrons. They are short of one electron to get nearest noble gas configuration and gain extra stability. Halogens require that one electron. They want to gain that one electron. So they act as good oxidizing agents because by gaining one electron they get nearest to noble gas configuration. So they themselves will undergo reduction, right? Now halogens are good oxidizing agent, that is understood, because they want that one electron to get nearest noble gas configuration. How this oxidizing power changes from top to bottom, that is from fluorine to iodine, how it changes. So what we are doing here, oxidizing agent gains an electron and itself undergo reduction. So here nothing but addition of electron to the neutral atom. Addition of electron to the neutral atom, it is nothing but again electron affinity. So does it follow electron affinity order? Let us assume based upon electron affinity order, the oxidizing power order, oxidizing power order, expected order based on electron affinity, the oxidizing power expected order is. So which element has highest electron affinity? Just now we have studied chlorine, then fluorine, then bromine, then iodine, right? But the observed order is fluorine greater than chlorine greater than iodine, right? So once again, halogens are good oxidizing agents, already we have studied, because they require that one electron to get nearest noble gas configuration. How it changes in the group? So what we are doing basically, the oxidizing agent gains an electron and itself will undergo reduction. Which element gains the electron readily? Nothing but electron affinity order. Based on electron affinity order, this is the electron affinity order. So, this should be the oxidizing power order, but the observed order is different. So, why fluorine is a powerful oxidizing agent than chlorine? Why the order has changed? Now, the answer is the oxidizing potential, oxidizing power does not only depend upon electron affinity. So, we just thought that it depends only on electron affinity and expected the order to be same. But the answer is the oxidizing power, oxidizing potential does not depend only upon electron affinity. It depends upon various other factors. So, let us see what is happening. So, the first point is the oxidation potential or the strength of oxidizing agent or the oxidizing power depends upon various factors. What are the various factors? First, I am taking halogen, half mole of X2. This can be in solid state because iodine is solid. So, I am writing for all the elements. X2 solid, first it will be converted into X2 liquid. X2 solid is converted into X2 liquid. So, conversion of solid to liquid, nothing but enthalpy of fusion. So, heat of fusion you can say. Enthalpy of fusion. This is the first step that takes place. Second step. Now we have liquid. The liquid is converted into gas, which we call it as heat of vaporization. So delta H vaporization. The third step, we got gas and it must be converted into X gas. So nothing but breaking the bond, XX bond. So we call it as bond dissociation energy. Delta H dissociation, and the next step is electron gain enthalpy. Electron affinity, and the last step is heat of hydration. Nothing but you have to dissolve in water. This takes place in aqueous solution. X minus aqueous, heat of hydration. Right. So the net energy, that is E, right, it is a sum of all this. So for this is for half mole, generally these values will be given for mole, but we are taking only half mole, so we have to divide it by half, because these values will be kilojoules per mole, that means for 1 mole, but we are taking only half mole here. Here also we are taking half mole. So delta H vaporization by 2 plus bond dissociation energy, delta H dissociation. This is also defined for mole. So here also we are taking only half mole, so dividing with the 2. Next, energy will be released, so minus EA. Heat of hydration, here also energy released, delta H hydration. So the sum of all these, because so the net energy is the measure of oxidizing power or oxidation potential. It is the measure of oxidation potential. So higher the net energy, higher will be the oxidation potential, higher the oxidizing power, stronger the oxidizing agent. So if I start with each element, fluorine is a gas, chlorine is a gas, both are gases. So these two are not necessary for fluorine and chlorine because they are already gases. So these two steps are not required for fluorine and chlorine. So leftover is, for fluorine and chlorine, leftover is these three values: delta H dissociation, electron affinity, heat of hydration. Fluorine, for fluorine, delta H dissociation is less compared to chlorine. Compared to chlorine, fluorine dissociation energy is less. Electron affinity is also less. Heat of hydration is very high. Compared to chlorine, for fluorine, fluorine has less dissociation energy, high heat of hydration. Now this value is positive, this value is negative. The net value, the sum of these two can compensate less electron affinity. Once again, fluorine has low dissociation energy, which is a plus point, and high heat of hydration compared to chlorine. These two can compensate the lower electron affinity, value of fluorine. Hence, fluorine net energy is more negative compared to chlorine. When I come to bromine, bromine is a liquid. For bromine, the first step is not necessary. For iodine, all the steps are necessary. So once again, fluorine is powerful oxidizing agent than chlorine. The reason is low dissociation energy and high heat of energy, which can compensate the lower electron affinity compared to chlorine. Therefore, fluorine oxidizing power is greater than chlorine. Bromine, iodine have lower dissociation energy than chlorine, but their heat of hydration, electron affinity are much lower. So the net energy value will be much lesser compared to chlorine. Hence, the correct order is fluorine oxidizing power is greater than chlorine, chlorine greater than bromine, greater than iodine. So initially we thought that oxidizing power only depends upon electron affinity, and based upon we predicted this, which is found to be incorrect, because the oxidation potential or strength of oxidizing agent or oxidizing power doesn't depend upon single factor called electron affinity. It depends upon all these factors. The sum of all these factors, we call it as net energy, which is direct measure of oxidation potential. So more than energy value, higher will be the oxidation potential, and that is found more to be fluorine, right? So this is about oxidation potential. Now this is the table for all this process experimental values. So first one, halogen, delta H fusion, that is the first step, delta H vaporization values for second step, delta H dissociation for third step, electron affinity for the fourth step, heat of hydration values for the fifth step, net energy, the overall energy, which is the direct measure of oxidation potential. So more energy the released, higher will be the oxidation potential, stronger is the oxidizing power of the element, or stronger is the oxidizing agent. So more energy, it should be more negative. As you can see, the more negative is for fluorine, minus 766.4, minus 597.3, minus 537.4, minus 437.02. So which element has higher E value, more negative value is? The answer is fluorine. Why it has more? Based upon electronegativity, if you predict, see only electronegative values, minus 333 for fluorine, minus 349 for chlorine. So here it is very clear that chlorine has higher electron affinity than fluorine. Next one is bromine, next one is iodine, but the oxidation potential is the net value, it should be more and more negative. Now why it is more negative? See, the first two steps doesn't take place for fluorine, doesn't require for fluorine and chlorine because they are gases. So directly we are comparing the last 3. Electron affinity is less for fluorine, but this value, the energy required to break the bond is less for fluorine compared to chlorine. This much amount of energy is required to break a bond in chlorine. This much amount of energy is required to break the bond in fluorine. Which has lesser bond dissociation? The answer is fluorine. Heat of hydration is energy released. Remember this one, the first step, second step, third step, they are endothermic. Energy is absorbed. Here these two are exothermic. Energy is released. More and more energy should be released. Then only the formed compound will be stable. That is why we require more and more negative values. Dissociation, energy is absorbed, therefore endothermic. It should be lowest possible. If I compare these two, which has lowest energy possible? Fluorine. So this is a favoring factor over chlorine. Come to here, energy is released. More energy should be released. More energy released is for chlorine. So this is electron affinity favors chlorine. But that is not the end of the story. We have to even compare heat of hydration. Now heat of hydration is exothermic process. So energy is released. Where more energy is released? In the case of fluorine. So 2 factors favors fluorine. 1 factor favors chlorine. In simple language, the net energy released in heat of hydration and consumed in dissociation compensates the energy, the low value of electron affinity in case of fluorine. So if I combine these 3, the net energy released is more negative in the case of fluorine. Coming to bromine and iodine, the dissociation energies are less, so it is a favoring factor. Electron affinities are less, defavoring factor. Heat of hydrations are also less. So here the heat of hydration, which compensates for fluorine, low electronegativity, low electron affinity, doesn't compensate low electron affinity because it itself is less compared to chlorine, right? Hence the net energy value is much less compared to chlorine. Therefore they are weaker oxidizing agents. So final conclusion is the oxidizing power is higher for fluorine than chlorine than bromine than iodine. This is the order, and remember the oxidation power doesn't only depend upon electron affinity, it depends upon all these factors. You have to consider the net energy.